Hey guys, welcome back to Computational Biology with Python. In this video, we're going to do something a little different with computer vision. We're going to detect features. And so in this example, what we're going to do is we're going to detect corners, right? So one of my examples to leading into creating these videos was talking about how I wanted to detect angles of root curvature, right? Because I was looking at phototropism or gravitropism. And so I wanted to measure the ability of a root, how much it curves towards gravity or curves towards light in certain conditions. And so finding features like corners and things can help you deduce the curvature of that root. So we're going to do something, we're not going to use roots, we're going to use a little bit of a clearer example in this. But alright, so first thing, open a new notebook, and we're going to save this one as, I'm going to call it corner detection. Okay, so first things first, we're going to import, there we go, import CV2, import numpy as np, and then we're going to import matplotlib.pyplot as plot. And so remember, these are just packages that we are using that are already built to give us the ability to do some of these things. So what I'm going to look for is a picture of a chessboard, and I don't want any borders or anything like that on it. So I found this green one in Wikimedia Commons. Whoops, I don't want to save the link. And I am going to save this into my pictures, chessboard, green, square. I'm just going to call it chessboard green. I don't need squares on there. Chessboard green. Okay. And then I'm also going to look for just a picture of a set up chessboard. Let's see. Let's do this one is perfect. So I'll say this as chessboard. Just chessboard, not green. Okay. So first thing I'm going to do is I'm going to say real chess equals cv2.imread, and I'm going to say or what did I call it? Chessboard. That's capital. Oh, first things first, I have to upload them, right? So first upload chessboard, and also upload green chessboard. So actually, first I'm not going to do the real chess. I'm going to do flat, oops. I'm going to do flat chess equals cv2.imread, and it's, what did I call it, green? Where is it? Chessboard green. .png. Alright, and then I'm going to say flat chess. Remember, we got to convert the colors because it's a JPG image. CV2, convert color, flat chess, cv2.color, capitalize color, bgr2rgb. 2, not at. And then I'm going to plot.imshow flat chess. Alright, perfect. So we have my green chessboard there, just what I wanted. But now we want to turn it to grayscale for this purpose. So we're going to say gray flat chess equals cv2 dot convert color, and we're going to say flat chess, two S's, CV2 color BGR to gray. And then actually, before we do it, let's do plot imshow gray flat chess. And our CMap, color map, is going to equal gray. And then in close parentheses. Wait, do we need to? This should be comma. Okay. Wait, gray flat chess. No, this should be an gray flat chess underscore. That's your problem. Gray flat chess, CMap gray. Okay. This should be not capitalized. Plot is not defined. Plot. Oh, PLT. There we go. Okay, beautiful. So we have a grayscale chessboard, which is going to be kind of our template to match something to. So now we're going to do our real chessboard image. So real chess equals cv2.imread, and what did we call it? We called it just chessboard.jpg. And then real chess equals cv2, convert the color, real chess cv2 color BGR to RGB. And so now if we plot imshow real chess, we should have a beautiful chessboard in the right colors. So now for the matching purposes, we don't want colors to get in the way of our object detection, so we want to create this in grayscale too. Real chess equals cv2 oh my gosh, color, and we say real chess cv2 color BGR to gray, and then we want to plot imshow gray real chess, and then our CMap is going to be gray. Beautiful. So now we have a black and white chessboard. So we have our test now and our flat one. So now we're going to use a method called Harris corner detection. So what we do is we say gray is equal to mp.float 32 gray flat chess, and we're going to say dst equals cv2 corner Harris, and our source is going to be gray, and our block size is going to equal 2. Our k size is equal to 3, and our k equals 0.04. So block size is the neighborhood size, so like how far out it looks from a prospective corner. K size is the kernel size, or K size is the aperture parameter for a Sobel operator. What that means is a little above my pay grade, but you can play with the values and see how the detection changes. So now what we're going to do is dst equals cv2.dilate dst, and we're going to say none. And should be src, not scr. So source cv2, it's probably dilate, not dilate. Sweet. Okay, so now we're going to say So whenever the result of our corner Harris, the DST command we created, is greater than, what will we have set? For 1% of the max value, it'll be assigned to the color red. So if we do flat chess, DST greater than 0.01 times the distribution of DST max, and we say equals 25500, and then we say plot imshow flat chess. So what we're saying is, okay, use our DST corner Harris detection to look at our flat chessboard, remember, which was this one, and we're going to say, okay, now anytime you detect a corner, to make it red. So as you can see, it's kind of, I'll zoom in a bit. You can see now all the corners here have been detected as with these red dots, right? So it's perfect for what we want this to do. Okay, so now we're gonna introduce a bit of noise, right? Because we're gonna use a real chessboard. Okay, so now what we're gonna do is we're gonna try it on the real chessboard. So there'll be some noise added, right? Because this is like the top-down view is a very basic example. So NP float 32 gray real chess. Dist equals CV2 corner Harris. SRC equals gray again. Block size equals 2. K size equals 3. K equals 0.04. Oh, not minus. Equals 0.04. DST equals CV2 dilate. DST none. And then we're going to say real chess, real underscore chess, DST greater than 0.01 times DST max equals, and so what we're doing, 255, when we do this 25500, that's just the color. So we're saying use all red and no other color. So if you did 02550, it would be all green, right? Or I think. And then if it was 00225, it would be all blue. That's how I remember correctly. But we're just doing red. You can use whatever color you want. Yeah, so it's just the hexadecimal or whatever they call it for colors. Okay, no typos. Hey. All right, so let's look at this. So as you can see, we've done a great job in the areas that are not, or that are the chessboard. The chess pieces, however, there's a lot of noise, and you can especially see it where there is the shine on the shiny black chess pieces, right? Because it's looking at where there is these distinct changes in color, right? And like edges like that. So there are corners where this white shine would be, and you don't see it as much on the white pieces because it's not as distinct or not as big of a change in it's not as stark of a difference between them. So let's do one more thing. We're going to use one more method. So that was the Harris, what did we call it? The Harris corner detection. This is shy. Here, I'll write this one down. Shy. Oh, Maybe. What's going on here? We freeze? There we go. Shy. My cursor's being shy at the moment. Oh. Alright, come on, baby. There we go. Shy. Tomasi. Corner detection. So, as you can see, there's different methods, and so unless you really want to get into the weeds with the math of it, which is, like I said, a little bit above my pay grade, it might be best to just try different methods and see if you can fine-tune the methods. Like, you could change that K size, and you can change your input images and things like that to find the method that best works for you for these type of computer vision algorithms. Because you don't have to be a computer scientist to utilize these tools. Alright, so flat chess equals, oh no, we already did the, let's see, we don't have to reload the images. Okay, so let's do, for this we'll do corners equals CV2 dot good features to track gray flat chess 64 0.01 10. So for this we are detecting the max level of parameters. We are detecting the 0.01 is just like before, like the quality level, and then for 10, the last part is the minimum distance. Okay, so now we've got our corners algorithm. So now we want to do corners equals np dot int 0 corners. And then we're going to say for I in corners, x, y equals I dot ravel cv2 dot let's move this down, cv2 dot circle flat chess x, y 3, and then we're going to give it our color, so we'll do red 255 0 0 -1. Okay, and then we're going to do down here plot dot im show flat chess. Let's hope this runs. Okay, beautiful. So you can see that we have all of our corners detected. We've got 1, 2, 3, 4, 5, 6, 7 times 1, 2, 3, 4, 5, 6, 7. So we've got 49 edges that we detected. All right, so this one looks, I mean, this looks just as good as the last one, right? But let's see how it works on the real chessboard. So corners equals CV2 good features to track gray real chess 100 0.01 10, and we're going to do corners equals np dot int 0 corners. We're going to say for I in corners x, y equals I ravel. So this is just the same thing, but we're just changing our input, right? CV2 dot circle real chess x, y 3, and we're going to do 0 to 55 0. So we're changing the color just to see what color that becomes. And then plot show real chess. Okay. Oh, this is supposed to be underscore here. There we go. So you can see we have green dots for this method of detection. Here, let's try running it now. Let's see. So this is an overlap of the two, right? So we added to the corners, or to the image, real chess, these additional greens. So you can see that there's a lot less green than there is red. And so this is doing a little bit better job. It didn't detect corners on the edge here for the green, but it did very good job on all the corners, and you can see it has a lot less red on the chess pieces. So this is a little bit more of a conservative approach to detecting corners. And like I said, for these type of things, like, you don't have to be a computer scientist to utilize these tools. It's the better you understand them, the better, you know, at applying them and fine-tuning them and whatnot. But really, it's a tool that, like most bioinformaticists, don't. I would say most. That'd be my guess. Don't understand the algorithms very deeply for sequence alignment. It's, you know, I had the pleasure to go to a workshop with Tice Brown, who is a he calls himself a K-merologist at the time. I think he used to be at Michigan State. He's at, like, I don't know if he's at Berkeley, somewhere in California, Berkeley maybe. But he is the guy that writes these algorithms for putting together genomes. And then once him and his colleagues and those type write these algorithms, then we apply them, right? And so I don't know the real heavy-duty math. I understand the process, but all the math behind it is a little less in my wheelhouse. I just apply the tools. And so, and that's the same thing with, for example, if you were to use a HPLC or some machine in your lab, where you might not know how every piece of the machine works, but you still know how to use it. And that's kind of the thing, right? Is knowing how to use these and not necessarily being a master of all the stuff behind it. That's just my opinion. Anyways, I'm rambling on. That's edge detection. And so we are going to do a couple more probably of the CV stuff, but you can see the utility in this and being able to detect changes in a picture. And then that's a feature, right? So I could detect changes in the pixel color for my roots to identify the root and measure a curve as opposed to a corner. And so this type of automated phenotyping can be useful in your science, in your biology. So with that, I hope you enjoyed the video. If you're watching on YouTube, please hit like, please hit subscribe, and I'll catch you in the next video.